In a typical 415-volt power distribution system, the supply feeder is typically 415/240 volts Y. This means that the three-phase voltage between any two phases is 415 volts, while the phase-to-neutral voltage is 240 volts. You can power 240-volt motors directly from a 415-volt supply if the motors are designed to operate on 240 volts. This method is commonly used in industrial and commercial settings. For powering 240-volt motors directly from a 415-volt supply, you will need a two-pole breaker connected to the hot and neutral terminals of the motor circuit. A common trip mechanism is required to ensure that both poles of the breaker open simultaneously in case of a fault. Always check the motor nameplate to ensure it is rated for 240-volt operation. Verify that the motor wiring is compatible with the phase-to-neutral voltage of 240 volts. Ensure that the load on the 415-volt supply is balanced to avoid voltage imbalances. Alternatively, you can install a 415/240-volt step-down transformer to supply the 240-volt motors. This method may be necessary if the motors are not rated for 240-volt operation or if there are other voltage-sensitive equipment in the circuit. The Y configuration is a three-phase system where the three-phase windings are connected in a Y shape. The neutral point is the common connection of the three windings. The voltage between any two phases is the phase-to-phase voltage, which is 415 volts in this case. The voltage between any phase and the neutral point is the phase-to-neutral voltage, which is 240 volts in this case. The phase-to-neutral voltage is derived from the phase-to-phase voltage by dividing by the square root of 3, so 415 volts divided by the square root of 3 equals approximately 240 volts. Powering 240-volt motors directly from the 415-volt phase-to-neutral supply is an acceptable and common practice when the motors are rated for 240-volt operation. It avoids the need for a step-down transformer, which can save cost and space. However, it's crucial to ensure the motor's voltage rating matches the supply voltage. When using a two-pole breaker, both the hot and neutral conductors are protected. In the event of a fault, such as a short circuit or ground fault, the breaker will trip and disconnect both conductors, providing a high level of safety. A one-pole breaker only protects the hot conductor, leaving the neutral conductor unprotected. Using a two-pole breaker is generally recommended for 240-volt circuits, especially when the neutral conductor is part of the circuit. To ensure the motor is rated for 240-volt operation, carefully examine the motor's nameplate. The nameplate will list the motor's voltage rating, which should match the supply voltage. If the motor is not rated for 240 volts, it should not be powered directly from a 415-volt supply without a step-down transformer. Ensuring the motor wiring is compatible with the 240-volt phase-to-neutral voltage is essential for safe and reliable operation. Check the wire insulation rating to ensure it can withstand the voltage. Use appropriate connectors and terminations to ensure a secure and reliable connection. Balancing the load on the 415-volt supply is important to avoid voltage imbalances. Voltage imbalances can cause motors to overheat and fail prematurely. Distribute the 240-volt motor loads evenly across the three phases of the 415-volt supply. Use a three-phase power analyzer to monitor the voltage and current on each phase and identify any imbalances. If the motors are not rated for 240-volt operation or if there are other voltage-sensitive equipment in the circuit, a 415/240-volt step-down transformer may be necessary. A step-down transformer will reduce the 415-volt supply voltage to 240 volts, providing a safe and reliable power source for the 240-volt motors. Select a transformer with a sufficient kVA rating to handle the total load of the 240-volt motors. Install the transformer in a well-ventilated location to prevent overheating. Connecting 240-volt loads to a 415/240-volt Y system requires careful consideration of several factors to ensure safety and proper operation. Firstly, verify the motor voltage rating on the nameplate. Secondly, use a 2-pole breaker for both hot and neutral wires. Thirdly, balance the load across all 3 phases. The typical 415-volt power distribution system, often found in industrial or commercial settings, indeed uses a 415/240-volt Y configuration. This configuration provides both 415 volts between phases, suitable for 3-phase equipment, and 240 volts between each phase and neutral, which can be used for single-phase loads if properly managed. Powering 240-volt motors directly from the 415/240-volt Y system, utilizing the phase-to-neutral voltage, is an acceptable and common practice, provided the motors are specifically designed and rated for 240-volt operation. This approach eliminates the need for individual step-down transformers for each 240-volt motor, simplifying the installation and reducing costs. When directly powering 240-volt motors from the 415/240-volt Y system, it is crucial to use a 2-pole breaker. This type of breaker protects both the hot phase and neutral conductors. In the event of a fault, such as an overcurrent or short circuit, the 2-pole breaker will simultaneously disconnect both conductors, ensuring complete isolation of the motor and preventing potential hazards. A 1-pole breaker, on the other hand, only protects the hot conductor, leaving the neutral conductor vulnerable to fault currents, which could lead to equipment damage or safety risks. Several additional considerations are paramount when implementing this configuration. Firstly, confirm the motor voltage rating. Secondly, ensure proper wiring. And thirdly, balance the load. Always verify the motor's nameplate to confirm it is rated for 240-volt operation. Supplying a motor with a voltage higher than its rating can cause damage, overheating, and premature failure. The motor's wiring and insulation must be appropriate for the 240-volt phase-to-neutral voltage. Using undersized or improperly insulated wiring can lead to voltage drops, overheating, and potential fire hazards. Ensure the wiring is installed in accordance with all applicable electrical codes and standards. Balancing the load across the 3 phases of the 415-volt system is essential for maintaining voltage stability and preventing imbalances. Uneven loading can cause voltage fluctuations, which can negatively impact the performance and lifespan of motors and other electrical equipment. Distribute the 240-volt motor loads as evenly as possible across the 3 phases to minimize voltage imbalances. An alternative to directly powering the 240-volt motors from the 415/240-volt system is to use a 415/240-volt step-down transformer. This transformer converts the 415-volt 3-phase voltage to a 240-volt 3-phase or single-phase voltage, providing a dedicated 240-volt supply for the motors. This approach may be necessary if the motors are not rated for 240-volt operation or if there are concerns about voltage imbalances or other power quality issues. A step-down transformer offers several advantages. Firstly, it provides voltage isolation. Secondly, it stabilizes voltage, and thirdly, it provides scalability. It isolates the 240-volt motor circuits from the 415-volt system, providing an additional layer of safety. It can help stabilize the voltage supplied to the motors, ensuring consistent performance. It allows for easy expansion of the 240-volt motor system without affecting the 415-volt system. In summary, powering 240-volt motors directly from a 415/240-volt Y system is a viable option provided the motors are rated for 240-volt operation and the appropriate safety measures are implemented. Always use a 2-pole breaker to protect both the hot and neutral conductors and ensure the load is balanced across the 3 phases. If these conditions cannot be met, a 415/240-volt step-down transformer may be a more suitable solution. NEC Section 430.22 provides guidance on motor circuit conductor sizing, specifying that the conductors supplying a motor must have an ampacity of not less than 125% of the motor's full load current rating. This ensures that the conductors can handle the motor's starting and running currents without overheating. NEC Section 430.52 details the requirements for motor branch circuit short circuit and ground fault protection. The type and size of the overcurrent protective device, such as a circuit breaker or fuses, must be selected based on the motor's full load current rating and the type of motor. The overcurrent protective device must be capable of protecting the motor and the branch circuit conductors from short circuits and ground faults. NEC Section 430.53 covers the use of several motors on one branch circuit, outlining the conditions under which multiple motors can be connected to a single branch circuit. This section specifies the requirements for the overcurrent protection, conductor sizing, and control devices to ensure the safe and reliable operation of multiple motors on a single circuit. NEC Section 430.7 provides requirements for motor nameplate markings. The motor nameplate must include essential information such as the motor's voltage rating, full load current rating, horsepower, and other pertinent data. This information is crucial for selecting the appropriate wiring, overcurrent protection, and control devices for the motor. When working with electrical systems, always follow safe work practices. Firstly, de-energize circuits before working on them. Secondly, use appropriate personal protective equipment, and thirdly, inspect equipment before use. Always de-energize and lock out electrical circuits before working on them to prevent accidental energization. Use appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools to protect yourself from electrical hazards. Inspect electrical equipment and tools before use to ensure they are in good working condition and free from defects. In addition to the NEC, other standards and regulations may apply to motor installations depending on the location and application. These may include local electrical codes, industry standards, and equipment manufacturers' recommendations. Be sure to familiarize yourself with all applicable standards and regulations before starting any electrical work. Using a 2-pole breaker for 240-volt motor circuits is generally recommended for several reasons. Firstly, it provides complete isolation. Secondly, it offers improved safety, and thirdly, it simplifies troubleshooting. It disconnects both the hot and neutral conductors in the event of a fault, providing complete isolation of the motor from the power source. It reduces the risk of electric shock and other electrical hazards by ensuring that both conductors are de-energized. It makes it easier to troubleshoot electrical problems by allowing you to isolate the motor from the rest of the circuit. To balance the load across the 3 phases of a 415-volt system, distribute the 240-volt motor loads as evenly as possible across the 3 phases. Measure the current on each phase using a clamp meter or power analyzer. Adjust the distribution of the loads as needed to achieve a balanced current flow. Avoid connecting all of the 240-volt motors to a single phase, as this can cause a significant voltage imbalance. Consider using a phase rotation meter to ensure that the phases are properly connected. The NEC provides specific requirements for grounding electrical systems to ensure safety and prevent electrical shock hazards. Grounding involves connecting non-current carrying metal parts of electrical equipment to the earth, providing a path for fault currents to flow back to the source and trip the overcurrent protective device. The NEC also addresses the use of ground fault circuit interrupters, or GFCIs, in certain locations to provide additional protection against electric shock. GFCIs are designed to detect small imbalances in current between the hot and neutral conductors and quickly de-energize the circuit, preventing a potentially fatal electric shock. GFCIs are typically required in areas where there is a high risk of exposure to moisture, such as bathrooms, kitchens, and outdoor locations. Selecting the appropriate size and type of overcurrent protection device for a 240-volt motor circuit is critical for protecting the motor and the circuit conductors from damage due to overloads and short circuits. The overcurrent protection device should be sized based on the motor's full load current rating, as specified in the NEC. The type of overcurrent protection device, such as a circuit breaker or fuses, should be selected based on the motor's characteristics and the application. Circuit breakers are generally preferred for motor circuits because they can be easily reset after a trip, while fuses must be replaced. When installing a 415/240 volt step-down transformer, it is essential to follow all applicable codes and standards. Firstly, ensure proper ventilation. Secondly, provide overcurrent protection, and thirdly, install grounding. Ensure the transformer is installed in a well-ventilated location to prevent overheating. Provide overcurrent protection on both the primary and secondary sides of the transformer to protect it from overloads and short circuits. Install proper grounding connections to ensure the safety of personnel and equipment. When dealing with motors, understanding motor starting methods is very important for the proper operation of the motor, the distribution system, and voltage impact on other electrical equipment. Firstly, across the line starting. Secondly, reduced voltage starting, and thirdly, variable frequency drives. Across the line starting connects the motor directly to the power supply, providing full voltage to the motor terminals. This method provides the highest possible starting torque but causes high inrush current that can affect the electrical distribution system. Reduced voltage starting methods such as auto transformers, reactors, or part winding starters are utilized to reduce the inrush current when starting motors. Variable frequency drives, or VFD, are used to control the motor speed and provide soft starting capabilities. VFD allow the motor to gradually increase speed, which reduces the inrush current and provides smooth acceleration. When working with motor control circuits, understanding the various components and their functions is crucial for proper operation and troubleshooting. Firstly, contactors. Secondly, relays, and thirdly, overload relays. Contactors are electrically controlled switches used to switch power to the motor. Relays are used for control and protection functions. Overload relays are used to protect the motor from overloads and overheating. Understanding the different types of motor enclosures is essential for selecting the appropriate enclosure for the specific application and environment. Firstly, open drip-proof enclosures. Secondly, totally enclosed fan-cooled enclosures, and thirdly, explosion-proof enclosures. Open drip-proof enclosures are designed to protect the motor from falling objects and dripping liquids. Totally enclosed fan-cooled enclosures are designed to protect the motor from dust, moisture, and other contaminants. Explosion-proof enclosures are designed to contain an internal explosion without igniting the surrounding atmosphere. When working with 415 volt and 240 volt systems, it's important to be aware of the potential hazards and take appropriate safety precautions. Always energize and lock out circuits before working on them. Use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. Follow all applicable electrical codes and standards. Seek guidance from a qualified electrician if you are not comfortable working with electrical systems. The 415/240 volt Y system is a common power distribution system used in many countries around the world. It provides a versatile and efficient way to supply power to both three-phase and single-phase loads. When working with this system, it's important to understand the voltage relationships between the phases and neutral and to follow all applicable safety precautions. The information provided in this narration is intended for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before making any electrical installations or modifications. Incorrect wiring or improper installation can lead to serious injury or property damage. Ensure that all electrical work is performed in accordance with all applicable codes and standards. If you are not comfortable working with electrical systems, seek assistance from a qualified electrician. The NEC is a comprehensive set of standards for electrical installations in the United States. It is updated every 3 years to reflect changes in technology and safety practices. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is an essential resource for electricians and other electrical professionals. When working with electrical systems, it's important to stay up to date on the latest changes to the NEC. The NEC can be a complex and challenging document to understand. If you have any questions or concerns about the NEC, seek guidance from a qualified electrician or electrical inspector. The information provided in this narration is based on commonly accepted electrical practices and the NEC. However, it is important to note that local codes and regulations may vary. Always consult with your local electrical inspector to ensure that your electrical installations comply with all applicable requirements. The safety of personnel and equipment should always be the top priority when working with electrical systems. Take the time to understand the potential hazards and follow all applicable safety precautions. Seek guidance from a qualified electrician if you are not comfortable working with electrical systems. Remember, electricity can be dangerous if it is not handled properly. Always exercise caution and follow safe work practices.